Hello, and welcome to your second linear regression lecture. The first thing I want to start off with today is a bit of a warning of something you don't want to do. Let's take a look at this data here. We have a bunch of data with a single predictor and a single outcome, and we fit a linear regression model to it. As you can see, our model's not perfect, but it's doing a pretty good job of describing this relationship. Now, what if we wanted to make a prediction for a value of x that's up here? Now, we can do this. Nothing in our model is going to stop us from making a prediction. In fact, our prediction will be this value right here. But one thing we need to be really careful about is extrapolation, which is what's happening here. We're making a prediction for a value that is very different than the values that we used to actually create the model. For instance, when we created our model, our values of x were kind of in this range right here, and we're asking our model to make a prediction for a value all the way out here. Now, the model will still make a prediction, but will it be a good prediction? The problem with extrapolation is we just don't know. Does the relationship we modeled continue even for larger x's, or does the relationship actually change at that point? In this case, we have a set of data where that relationship did change. The relationship gets a lot flatter than it was in our initial values. This makes our prediction way up here look pretty silly. In fact, our prediction should probably more be like here. This is happening because we're using our model to make predictions about a value that is very dissimilar to the values that we trained our model on. If we had had the full range of data, we might have fit a model more like this. So always be careful with extrapolation. Make sure you're making predictions for values that are similar to the ones that we've trained our model on. For instance, I wouldn't make a model predicting healthcare costs on people who are like in their 20s and 30s and then think that that's going to make accurate predictions for someone in their 80s. But we just saw in our extrapolation example that we had a variable that had a non-linear relationship. And as we know from the previous lecture, linear regression assumes linearity. So what do we do if there is non-linearity? Are we just out of luck? Luckily, we're not. And today I want to talk about a couple of different ways that we can fit non-linear relationships while still technically using linear regression. To do that, we're going to talk about feature engineering. Now, feature engineering is a broader term that applies beyond what we're talking about today. But in general, feature engineering basically means that you, the person working with the data, are going to create new features for the data. For instance, if these gray columns are values that we already had in our data, feature engineering would be creating new values to add to our data. These values can then be used as predictors in our model. Now, you might say, well, so what? If we create new values, it doesn't really solve the problem of nonlinearity, but it actually does in a way. There's two main methods that we're going to talk about in this course that allow us to fit nonlinear relationships while still technically using some form of linear regression. The first one we're going to talk about today, which is creating new features, that feature engineering we just talked about. The other one we'll save for our logistic regression lectures. So let's take a look at this data. Here we see a very simple problem where we have one predictor on the x-axis and it's predicting one outcome on the y-axis. Now, this has a very clearly non-linear relationship. In fact, if I saw this data, I would say it's violating the assumption of linearity. You can even see here when we fit a linear regression that it does a pretty poor job of explaining the relationship between our input x and our output y. That's because this form of linear regression that we have is just not complicated enough to fit this data. But what if we created a new feature? And what if that feature was our original feature squared? All we're doing here is we're basically creating a new column in our data where the value of that column is our original predictor squared. Then we take that column and we use it as a predictor in our linear regression model. Now, we're still doing linear regression, and this is where the term linear in the parameters comes in, which is something data scientists and statisticians say a lot. What this means is that this is still a linear regression. All of the parameters, like the coefficients that we have, are still linear. We're not like taking them to a square or taking the log of them. They're still linear linear in the parameters. But our predictor, well, one of them, is now a squared variable. And when we look at this on the original scale, it allows us to make nonlinear predictions, see this curved line, while still technically being a linear regression. Now, this line fits our data a lot better, but we don't have to stop there. We could also add an x cubed. Again, this is just like adding two new columns to our data frame, where one of the columns is our original predictor squared and the other column is our original predictor cubed. Again, we're still just doing linear regression, but our predictions end up being nonlinear. If we look at this, we have now a cubic curve, and this actually almost perfectly fits the relationship in our data. This practice is called polynomial regression, where we take our predictor or predictors and we take them to different powers, essentially doing feature engineering, creating new columns of our predictors to the second, third, fourth, etc. power. The degree of the polynomial, here it's 3, is the number of powers that we take something to. So if the highest power we take our predictor to is 3, then we would say that is a polynomial regression with degree 3. One thing you need to be a little bit careful about with polynomial regression is making sure that you don't have too high of a degree. For example, here is a polynomial regression with 25 degrees. You can see that this gives us a pretty wonky curve that's kind of all over the place, and honestly at this point we as humans can see that it's not doing the best job of explaining the relationship between our input and our outputs. But again, technically possible. You just want to be careful to make sure that you're using enough degrees to be flexible, but not too many degrees that your equation looks like this. So again, to review in the framework of using feature engineering, all we're doing is we're taking one original variable and we are creating new columns with it, essentially engineering features. And these columns are just that original predictor to the second, third, fourth, etc. power. Another thing we can do with feature engineering is add interactions. Interactions answer the question, is the relationship between x and y different when we consider a third variable, z? For instance, here we have a predictor x and an outcome y, and we have another categorical variable z, where one category of z is shown here and the other is shown here. Here we have no interaction. This means that the relationship between our input x and our output y is the same no matter what value of z a data point has. You can see this by the fact that the slopes of these two lines are the same. While group 1 might have higher y values on average, the slope is the exact same for group 0 and 1. This means that there's no interaction, but what if there was an interaction? In fact, you can even see if you sort of squint your eyes and look at the background data that it's very likely that these two groups do not have the same slope. This model with no interaction has our typical form. It has an intercept, it has a slope for the predictor x, and then a slope for the categorical predictor z. But what if we wanted an interaction? Well, here we're seeing an interaction because the slope of our two lines is different, one for group 0 and one for group 1. But how could we add this to our model? The way we do it is technically with feature engineering. What we're going to do is we're going to create a new variable that is our two predictors multiplied together. Now, what's really interesting about this, especially because z is a binary variable, although it works for all types of variables, is that when z is 0, this entire term gets canceled out. But when z is 1, this term is added back in. Essentially, this term is an adjustment that we make to our slope when our value is in the category z equals 1. This allows our slopes to be different. And again, this is just feature engineering. We're basically creating a new column where that column is the value of our two predictors, x and z, multiplied together. then we can just add that to our linear regression. And we don't have to just stop with two-way interactions. If we have more variables, we can do two-way interactions or three-way interactions. All we're going to do is create new columns where it's two or more of our predictors multiplied together. Then we just fit a typical linear regression with these new columns. Another way that we can add nonlinearity through feature engineering is with step functions. Step functions look like steps, and basically what's happening is we're taking different ranges of our predictor x and we're fitting a line for each of those ranges. Here you can see that happening a little bit more clearly. So what's happening is we have a range from here to here, and this line is basically the average value for that range. Then we look at the next range from here to here, and we have the average value for that range, and so on and so forth for all of the ranges. Now we can see, even though it looks a little weird with all of the steps, we technically have some nonlinearity. Now, what's happening behind the scenes when we do that is we're basically creating dummy variables that indicate whether a data point is in each of our ranges. So for instance, this might indicate whether or not it's in the first range, and this might indicate whether it's in the second range, and so on and so forth. So we create a bunch of 0, 1 dummy variables that indicate which range our variable is in. Then we fit our model using those dummy variables. This allows us to get this step behavior. Now, a good way to think about everything we've learned in a more general form is with something called a basis function. Basis functions basically say that we could have a linear regression where instead of fitting on the raw predictors, we're fitting on a transformation of that predictor. When we were looking at polynomial regression, that transformation was basically taking our variable to different powers. When we were doing our step functions, our transformation was using an indicator variable. An indicator variable just indicates with a 0 or a 1 whether a value is between some range. So we created multiple of these indicator values and used those as predictors in our models. Again, basis functions are just a general way of thinking about a lot of the stuff that we've already been doing. And the functions that we use for basis functions don't have to just be step functions or polynomials. We could also use sines or Fouriers or whatever it is that we want to use as our function to transform our original variables. Now that we have that generalization, let's combine some of the things that we've seen in order to have an even more flexible type of model called a spline. Splines basically take the idea of a step function and a polynomial and combine them together. Basically what we do is we take our predictor variable and we split it into different ranges, just like we did with step functions. For instance, here in these images, you can see that we have two ranges, one on the left and one on the right. Then in each of those ranges, we fit maybe something like a polynomial regression. Here we're using cubic splines, which means that in each of these ranges, we're fitting a model with up to x cubed. And it can really be as simple as that. For instance, in this image, that's what we're doing. We're fitting a cubic model in each of our two sections of our predictor. But we can also get a little fancier and put some constraints on that. For instance, this looks a bit weird that your prediction jumps when you move past that line. So one constraint that we can put on our spline is that it has to meet in the middle. For instance, here we have a restriction that the value on the line has to be the same on the left and the right side of the line so that they meet up. Another restriction we can have is not only that our value is the same for both sides of this line, but also that the first and second derivatives of the line match up so that we get a nice smooth function. One really nice thing about splines is that we can get a lot of flexibility with our model by having different ranges without increasing the degree of the polynomial that we're fitting. For instance, here you can see an example where we fit a cubic spline, remember cubed to the power of 3, that has a bunch of different ranges along our predictor age. You can see that our model is still pretty flexible even though we're only using a cubic spline, so degree 3. Compare that with a similarly flexible polynomial that has a much higher degree. In general, it would require a much higher degree of polynomial to get the same flexibility as a spline with a much lower degree. All right, let's take this generalization even further. Now, in this class, we're typically not going to be fitting spline models or GAMS, generalized additive models, but I want you to be aware of their existence. Generalized additive models, or GAMS, basically take the idea of a regression spline and generalize it even further. like we've seen before, a GAM basically assumes that we have a model that's linear in the parameters, but we basically take our input variables and we do some type of transformation to them. GAMs have a lot of extra fancy features that we're not going to go into here, but one nice thing that it does is it extends regression splines to multiple different predictors. So instead of just having the predictor age and we bin that into different ranges and fit different polynomials, we could have predictors of age and education and etc. For instance, here's an example of a GAM where we have 3 different predictors. We have a predictor of year, and this is basically like a spline here. We have a predictor of age, again, a different function, a different spline. And then we even have a categorical predictor called education. GAMs basically take the best of all of the methods that we've been talking about, combine them with some even fancier features to make sure the functions we fit are nice and smooth, and gives us a really easily fit, easily interpretable model while still having a ton of flexibility. Again, we won't be fitting GAMs in this class, but it's a great extension of the things we will be doing, like polynomial regression. So to review, we talked a lot today about feature engineering. We have a lot of cases where a simple linear regression model just won't do. For example, if we have nonlinearity. But we talked about a really cool workaround, which is feature engineering, where we take the existing inputs that we have for our model and we transform them in some way to create a different type of relationship, for instance, a nonlinear relationship, while still technically using linear regression. All right, that's all I have for you. I will see you next time.